My name is Drew Gronewold. I'm an associate professor here at the School for Environment and Sustainability at the University of Michigan, and I also have a joint faculty appointment in the Department of Civil and Environmental Engineering. Water levels across all of the Great Lakes have either just recently set all-time record highs or are about to come close to either highs for this time of year or all-time record highs. Part of why that's significant is the water levels go through a typical seasonal cycle where they rise in the spring, peak in the summertime, and then decline in the fall. So right now we're at that time of year where water levels are already at the peak for the season. The fact that they're setting these all-time records means that there's extensive flooding and a lot of problems around the region. So Great Lakes water levels go up and down in response to two primary factors. The first is the amount of precipitation that falls on the region. That contributes, of course, to increasing water levels. But then there's also expansive evaporation across the lakes. The Great Lakes are a massive freshwater surface area, really the largest collection of freshwater surfaces on Earth. So from that perspective, the amount of water lost through evaporation has a huge impact on long-term water levels. So over time, we can look at water levels and changes in precipitation and evaporation and track what's causing water levels to go up or down. Right now, what's happened is really a combination of two factors. First off, precipitation over the past year, as well as the past decade, has been well above average. So we're getting a lot more water coming into the Great Lakes Basin. But another interesting thing that happened, and this started in about 2014, is that evaporation rates slowed down, and they slowed down drastically. So essentially you have more water coming in, less water leaving. That leads to a net increase in water levels across the entire region. So in general, when we have maybe a little bit too much water or too little water, but it stays within a normal range, that might not be a problem. But right now we're in a period of overabundance of water. And so there are sort of two categories of problems that I would describe. One relates to things that are happening inland with rivers, streams, and soil moisture. So for example, when we have this much rain, this much of an overabundance of water, there can be very hazardous conditions, particularly in rivers and streams. For example, rivers and streams, the banks can get high, leading to erosion and unsafe conditions for humans. And also they can lead to damage to infrastructure, to stormwater systems, sewer systems, roads, and bridges. We also have problems with soil moisture across the region. Right now, soils are very wet. There's a lot of ponded water, and that makes it difficult for states like Michigan and others in the region to plant spring crops. And that's a major problem. Now, that's just on the inland side. Here in the Great Lakes region, of course, there are problems on the lakes as well, and we alluded to those a moment ago, but when Great Lakes water levels get this high, it's problematic as well. There are problems with coastal erosion, flooding of homes, and even unsafe conditions for people along the shoreline as well. So the University of Michigan is involved in several strong partnerships across the region that help understanding this story in terms of how precipitation is changing and even how the regional climate system is changing. One of the most important collaborations there is through the Cooperative Institute for Great Lakes Research. This is a joint initiative between the University of Michigan and NOAA, the National Oceanic and Atmospheric Administration, and both Wayne State University and Michigan State University are part of that partnership. And that Cooperative Institute looks at historical climate data, precipitation data, and importantly tries to translate that information into models. Models on a climate scale as well as hydrological models that can both simulate as well as forecast the relationship between changes in precipitation and temperature and changes in Great Lakes water levels. That's one important thing that University of Michigan is involved in. University of Michigan also contributes to the Great Lakes Integrated Science and Assessment Center. That's also a part of the National Oceanic and Atmospheric Administration. And that group, the acronym is GLESA, is working hard to pull together summaries of precipitation and other climate data to help people make better decisions about how they plan and interact with infrastructure, homes, and other facets of the landscape as well as on the lakes themselves. One of the things that I and my colleagues are focusing on a lot right now is the ability to forecast. We want to be able to anticipate, and we want to be able to provide predictions for citizens, for municipalities, for other stakeholders in the region to better understand what might happen with precipitation and water abundance, first on short-term timescales, on the range of, say, 5 days to 14 days to make better decisions, but also on seasonal timescales, on the time range of, say, 1 to 3 to 6 months out. And then finally, on longer timescales, on multi-decadal timescales, 10, 20, even 30 years out, there are a range of decisions that are made across all of those different timescales. So it's important to have forecasts that coincide with the timescales of those management decisions. And that's one of the most important things we're working on right now. If the frequency and magnitude of rain events starts changing over time, and in particular gets higher, there's an increased chance that we're going to exceed the capacity of those stormwater systems and send unwanted pollutants, not to where they're supposed to be, which is into wastewater treatment systems or back into the ground, but into surface waters, into rivers, streams, and the lakes. And that's not what we want, and that's a consequence of having systems that are designed for weather and climate patterns under one regime, but they haven't adapted or been updated yet for a new regime. We talked earlier about these consortiums that already exist, GLISA and SIGLR, particularly with the Cooperative Institute, Wayne State and Michigan State and the University of Michigan, who make up the University Research Corridor, are part of that collaboration. More generally, the resources at these three universities are so important in terms of answering this question and pulling together those resources to answer this long-term question. I'll give one specific example. Scientists at Michigan State University are doing incredible work right now on groundwater modeling. Similarly, at Wayne State, there are a lot of experts in policy and law analysis, and we partner with many of them to answer these questions and tie the science that's being done, the modeling and the forecasting, into laws and policies that can ultimately, hopefully, lead to better decisions. What we found is we've been contacted by scientists and federal agencies in Africa, particularly in Malawi and on the other large lakes in the area, because they are finding that there's an urgent need to understand water level fluctuations. In the Great Lakes, we've been studying Great Lakes water level fluctuations for quite some time. In Eastern Africa, there's a slightly different story in that low water level conditions on many of the lakes, not just Lake Malawi, Lake Tanganyika, but some of the other large but smaller lakes, are leading to problems with fish harvesting. And that's a major source of protein for those areas. So we've been contacted and we've been starting a partnership specifically on hydrology and water levels to translate a lot of what we learned about the Great Lakes here in North America to help solve water level problems there in Africa. I did spend some time in Malawi earlier in May to launch that collaboration, and we're looking forward to continuing over the next several years. In terms of solving some of the problems, we talked about how do we better anticipate problems with, say, climate change or precipitation. One of the things that we're doing here at the University of Michigan, and I think is being done throughout the University Research Corridor, is to develop students and even faculty and staff with a better appreciation and understanding for the entire Great Lakes system. The state of Michigan is a wonderful state, and it's deeply connected with the Great Lakes, but the Great Lakes as a whole involve a connection between 8 states in the United States, 2 Canadian provinces, and even First Nations and lands that belong to tribal territories. So there's an important story that we need to be telling both among the institutions and to the students that we're moving forward about the entire Great Lakes system and how important it is to understand it and make good decisions about how we use it. In general, there are a lot of future climate simulations for the Great Lakes that try to answer questions about long-term trends. Now, I'll pause there to mention that that's a very, very challenging task, in part because there's so many dynamics between the land surface and the water surfaces, say, for example, with lake effect snow, that make it hard to predict 50 years from now what is the lake surface and lake depth temperature going to be. That said, most of the climate projections that we've seen indicate the lakes are likely to continue warming, although there's a very strong seasonal pattern to that temperature cycle. So they're expected to be warming in different times of the year at different rates. I've also seen the fact that it's expected that on average, ice cover is expected to diminish, although it's important to note that there's also expected to be a lot of variability around that long-term trend, as we've seen just over the past 10 to 20 years, where ice cover has been low, but then we have years where ice cover is very high. Now, to answer your question more directly about the relationship between precipitation and evaporation, it is indeed true that in general you'd expect with warmer water to have more evaporation. But by the same token, with a warmer atmosphere, we're actually carrying more moisture into the region, and that's why precipitation rates in general are going up. So we have this trade-off between increases in precipitation and increases in evaporation. And so to summarize, a lot of the models that we've seen that play out these different conditions, they don't really show a predominant trend towards either an increase in water levels because of precipitation winning out or a decrease in water levels because of evaporation sort of winning out. There really isn't that much of a departure in long-term water levels over, let's say, 20, 50, 80 years from what we've seen in the historical record. But it is important to note that what we are looking closely at is the amount of variability in water levels over that time period and how people can better adapt to that. When water levels reach an extreme, how extreme do they get in terms of highs, but also in terms of lows? Another part of that variability, though, is how quickly do water levels transition between those extremes and how often. One of the things that we're going through right now is that water levels declined most recently rapidly in about 1998. And on the upper lakes, Superior, Michigan, and Huron, they stayed persistently low until 2014. So you really can't find another period in the historical record where water levels had such low variability for a 15-year period. And then in 2014, what happened? Water levels rose at one of the highest rates in the historical record, and now here we are at these upper extremes. So again, it's definitely a part about when water levels get extreme, how extreme do they get, but also the transition between extremes is something that we're watching in terms of a change in the future versus what we've seen in the past.